Welcome back, everybody, to our series on flip-flops. This is going to be a clocked JK flip-flop. The assignment that we're doing is 5-11. It's similar, but notice that is a negative going transition, and that can be accomplished on this circuit by putting an inverter on a clock. So let's go ahead and start the simulation. As you can see, the initial state of everything right now is 0. Now in our text, in figure 5-24 on page 258, it shows the Q is starting off as true. So we're going to go ahead and set that. So now we're in the condition as demonstrated in the textbook. I'll go ahead and add a space just like we've seen in the past. Now let's go through this pattern. We've got a K, a C, a J, a C, a space, a C, a J, a K, a C, and a space, a C, a J, a C, a space, a C, a K, a C, a space, clock, 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 clock. So you'll see that this matches pretty well to the textbook and the results that they received. Now, I want to talk about this circuit a little bit further just to kind of further illustrate the function of this circuit. So again, I'm starting off with a blank slate, and the Q is false, and all the inputs are false. So, as you saw me demonstrate last time, to turn Q on, what I'm going to do is I'm going to enable J, and on the rising edge of the clock, that will set Q to true. As you can see, if I continue to clock it, there's no state change. If I click K, there's no state change. Again, it all depends on the rising edge of that clock. Now, this has an interesting function, and it's referred to as toggle mode. If J and K are both set to true, and we repeatedly toggle the clock, you can see that the output of Q is varying. And if you look below, you can see that the output of Q is going to be half of the frequency of the input of the clock. There's a lot of ramifications that we'll come across for this. In the next chapter, when we go into counters, you'll see some of the uses of a flip-flop like this. All right, thanks again.